Okay, cool. Like I said, we did when the standard deviation of the population is known, and then our next section, we're going to talk about when it's unknown and the different ways to construct this confidence interval. So we've already figured out how to construct one, but now we're going to talk about something like we're going to talk about sample size and how it's related to a confidence interval. So we're going to say, hey, if you want to be this confident about something, what sample size would you need to do that? Like how many people do you need to ask, or like how many samples do you need to gather in order to be this confident? So like, you know, the more people that you survey, maybe the more confident you can be that, I don't know, you've made a good conclusion or something. So this is going to kind of talk about working backwards, where normally we've been given a sample size and then we use it, but now we're going to work backwards and we're going to say, hey, this is how confident we want to be. So how many people do we need to ask? So, like the notes say, oftentimes we need to decide how big of a sample we need to make an accurate estimate of the population parameter. This is not easy because it relies on three things. So we need the maximum error of estimate, which is me saying, oh, this is how accurate I want to be. And then we want the population standard deviation. And then we also want the degree of confidence. So we have a formula for this. So let me go ahead and write it and fill it in. So our formula is, and oh wow, that is way too big. I don't know why I had this on an 8. Okay, so our formula is n equals, where n is going to be your sample size, equal to that z sub alpha over 2 times sigma over e squared, where e is the maximum error of estimate. So you'll see what that looks like when we do an example. But the other things in this formula you should be familiar with. And then we have a little note here that if your answer is not a whole number, you always want to round up. So never round down. So whenever you get a decimal as your answer, you always want to round up, because if you say, oh, I need at least 128.5 people, a half a person doesn't make sense. So you always want to round up, because we'd rather have one extra or a little more than a little less. Okay, so let's just do an example here. Okay, so example, a university dean of students wishes to estimate the average number of hours students spend doing homework per week. The standard deviation from a previous study is 6.2 hours. How large a sample must be selected if he wants to be 99% confident of finding whether the true mean differs from the sample mean by no more than 1.5 hours? Okay. So like I said, we've been given a few things about what we're looking for, and we know that he wants to be 99% confident. And this is the maximum error estimate down here, where it says by no more than 1.5 hours. So we want to know how big a sample size we need in order to be 99% confident that we're, you know, not differing by more than 1.5 hours from the true mean. Okay, so let's just identify what's what in my problem. So first of all, I've been given the standard deviation, which is sigma, and that's 6.2. And like I said, the maximum error of estimate, where E is 1.5. So I want to make sure that this doesn't differ by more than 1.5 hours. And then lastly, to figure out the sample size, I need Z sub alpha over 2, which kind of got to throw it back. I think it's in this thing. Let's see. Okay, here we go. This is our Z sub alpha over 2. So this depends on how confident you want to be. Our problem says he wants to be 99% confident. So our number associated with a 99% confidence interval is going to be 2.58. Okay, So this is 2.58, and then all that's left to do is fill these things into our formula. So n is equal to 2.58 times 6.2 over 1.5 squared. All right, and if we just plug this into our calculators, all right, I get 113.7. And like my instruction said, you always need to round up. So my answer is 114. What that means is if you would like to be 99% confident that the true mean does not differ from the sample mean by more than 1.5 hours, you will need to have a sample size of 114. Okay, and that's actually the last thing in section 7.1. So section 7.1 introduces confidence intervals, how to find them when you do know the population standard deviation, and then also how to figure out the sample size needed in order to be a certain degree of confidence in like an answer that you're giving. Okay, that's it on section 7.1. So any questions before I move on to 7.2? Okay, let's just go ahead and move on. All right, so like I promised, our next section would be on confidence intervals for the mean when your standard deviation is unknown. So last time we did the confidence intervals when we had the population standard deviation, but now we're going to do them when we don't know it. So this is going to be a similar process, but slightly different. So like our lecture notes say, when the standard deviation is known and the sample size is 30 or more, or the population is normally distributed, the confidence interval for the mean can be found by using the standard normal distribution. So when we were finding our confidence intervals, we were using those z-scores and we were using the tables and the standard normal distribution, and that's how we found those values. So we were able to, take how confident we wanted to be in something, use our normal distribution, find, some z-scores and work through all that. But that's when we knew the standard deviation. And when the standard deviation is unknown, we can no longer use the standard normal distribution. So no more z-scores. We're no longer allowed to use that chart. But don't worry, we're introducing a new chart and a new distribution, which is why I say it's not that different, but it is a little different. So this is what's called a t-distribution. So if you're trying to find a confidence interval and your standard deviation is unknown, we're going to use what's called a t-distribution. Not that different from when we use the standard normal distribution. I think you'll see how similar it is, but they are slightly different. Both of them have charts, but a little different. Okay, so now we're introducing this thing called a t-distribution. So we do have some characteristics of it, and it's got similarities to the standard normal distribution, and it also has some things that are slightly different. So first, let's talk about the ways that the t-distribution is similar. So one, it is bell-shaped, and if you look in the textbook, there's some images. I don't have one on my lecture notes, but it is bell-shaped as well. It is symmetric about the mean, so in the same way that the normal distribution is symmetric across the mean, this one is as well. The mean, median, and mode are all equal to 0 and are located at the center. So same thing with the standard normal. And the curve also never touches the x-axis. It just approaches it on both sides. So those things are all pretty similar. And that's a lot of the characteristics of the standard normal distribution. So far it's not looking too different. But the ways that it differs from the standard normal is its variance is greater than 1. So the standard normal always has a variance of 1, and this one's greater. So the t distribution is actually a family of curves. So with our standard normal distribution, we have that single bell curve, but the t distribution is actually what's called a family of curves. And like it says here, see page 383, and you can see a picture of what this looks like, and you can see like a bunch of them all on one graph. And the family of curves is based on the concept of something called degrees of freedom, which we are going to introduce. So it's based on that, but we haven't defined that yet, so it's okay if that makes no sense right now. And just note that the degrees of freedom are related to the sample size, extremely related, and I'll explain kind of what that means when we get there. And then another fact is that as the sample size increases, the t distribution will actually approach the normal distribution, the standard normal. So those are some ways that they're similar and different. Like I said, if you really want a visual, I recommend looking in the textbook because there's some good diagrams and graphs in there. But for now, just have an idea of the things that are on the lecture notes, and we're really going to practice applying the t distribution and using the chart. So that's what we're going to focus on. But those are some similarities about it. Okay, so let's introduce this thing called degrees of freedom, because we said that the t distribution has a family of curves that is based on something called the degrees of freedom. So let's actually define what that is. So the degrees of freedom are the number of values that are free to vary after a sample statistic has been computed. That might make absolutely no sense, but once you hear me give an example, I think it will make a little more sense. So it's the values or the number of values that are free to vary after a sample statistic has been computed. So I'm going to talk about an example. I don't even know if I'm going to write it because I think it would make more sense for me to verbally explain it. But so let's say we have 5 values. So, sorry. Okay, let's say we have 5 values, and we know that the mean of them is 10. So if you kind of think back to when we would do, or on the first exam, I gave you an example where I said, hey, give me 5 or 6 like data values or something that satisfy the mean being this, the mode being this, and the median being this. So you're kind of familiar with that. So if you have, we know we have 5 data values and the mean is 10. So let's say that's all we know right now. So if that's all you're trying to satisfy, so you've got 5 values with a mean of 10, you can really pick your first 4 values any way you kind of want. So I can really pick whatever I want for the first 4. They can vary, but once I get to picking the 5th value, it has to be a specific number because it has to satisfy the fact that the mean is 10. So I can really pick whatever I want for the first 4, but because it's got to satisfy that mean being 10, that one is not free to be whatever it wants. It has to be something that satisfies the mean being 10. So like, for example, if you have 5 values, so I'll actually write this out, this might be more helpful. So 5 values with a mean of 10. Okay, well, you're familiar with if it's a mean of 10, it means that when I add all these 5 values up and then divide by 5, I get an answer of 10. So that means that when I add my 5 values up, I should get a total of 50. So we know that when I add each of these points up, let's just call them like x1. We know that when I add them all up, I should get 50 because when I divide their sum by 5, I want to get an answer of 10. Okay, so let's just pick the first 4. So let's say I pick x1 is 5, x2 is, I don't even know, 3, x3 is 1, x4 is 2. Oh. Okay, so if I add these up, I have 5 plus 3 is 8, plus 2 is 10, and then plus 1 is 11. So far I have 11, but when I sum all my values up, I need to have 50. So I know that my last value needs to be 39. I don't have a choice. It has to be 39. Because if it's not 39, they're not going to sum up to be 50. And that doesn't satisfy the fact that the mean is 10. So that's what we mean when we say that there's like a number of values that are free to vary. But like right now, I have one that can't be whatever I want. So the first four you could pick and do whatever with, but the last one has to be the thing that satisfies the mean being 10. Hopefully that makes a little bit of sense. And for this reason, our degrees of freedom is one less than the sample size. So if you notice, I had 5 values and I was able to pick 4 of them, but one of them has to be that thing that satisfies the mean. So my degrees of freedom would be 4. So it's one less than the size of like the sample or the group or the number of values. So that's the number that I can just pick freely. So let's fill this out now. So the degrees of freedom for a confidence interval for the mean are found by subtracting 1 from the sample size. Okay, so that is how we find them. For the confidence interval, it's 1 less than the sample size. So just remember that, remember this example. So let's do some examples now. And shockingly enough, of course, we have a chart that we're going to. So with our last thing that we did with the z-scores, we were finding this value z sub alpha over 2. Well, now, shockingly enough, we're just finding this value called t sub alpha over 2. So it's not too much different. So sorry, my lecture notes didn't copy this over. Okay, let's do these examples now. So it says find the t multiplier, which is t sub alpha over 2, for a 98% confidence and 24 degrees of freedom. Okay, so you might look at that and be like, I don't know how the heck to find that. Well, don't worry, we have a chart. So let me show you the chart. And I posted this on Canvas, so you have access to it. It's also in the textbook. But I named it Z versus T distributions. So the first page is the stuff that we did with the z-scores, so the normal distribution, so that's old stuff. And then the next page is the t-distribution stuff. So this is the values that we're looking at now. So this is where we're finding that t sub alpha over 2. So you can see that the only things that you need to know is the confidence. So we've got 80, 90, 95, 98, and 99. Those are all our options. And then you also just need to know the degrees of freedom. That's D, DF, right? So our example said, find the T multiplier for 98% confidence. So I'm going to be looking in this column because I 98%. And I want 24 degrees of freedom. So I just come down the degrees of freedom thing, which is right here. And then I just see where these meet up. And they meet up at 2.492. So that is your multiplier. So like previously, we would find the like the z value, the z sub alpha over 2. But instead, now we just come to this chart, and this serves as your t sub alpha over 2. And it only relies on the degrees of freedom and the confidence. So we found this one. Okay, so this answer based on the chart was just 2.492. Okay, the next one wants you to find the T multiplier for 90% confidence and 17 degrees of freedom. So let's come back to our chart. Okay, so we want 90% and 17, oh, that was terrible looking, and 17 degrees of freedom. Okay, so I'm gonna let you guys use the chart, locate what this number would be, and then chat me your answer when you get it. We should all be pros at reading charts by now. Right on. Okay, good job, everyone. So yes, the answer for this one was 1.740. Hopefully everyone loves reading these charts off because this is like really one of the main parts of this next exam that's coming up. It's like everything revolves around these charts. So good job. That went well. So let me come back. Okay, so we found out that this was 1.740. Okay, so that's how you do that. And then there is a formula just like before. So shocker, to find the confidence interval, you really just need things that you'll be given in the problem and then that T multiplier value that we just found. So let me go ahead and write this formula in. So it is X bar plus or minus T sub alpha over 2 times S over the square root of n. So you'll notice that instead in this formula, we have S, which is the sample standard deviation. So remember when we were doing confidence intervals in the last section, we knew the population standard deviation. Well, in this case, we don't. All we know is the sample standard deviation. So that's why our formula has to change a little, and that's the difference between the two. And there is a handy little thing in your PDF. So actually, let me show you that really quick because I didn't mention it yet. If you go to the last page in this PDF that I posted, I copied in this little like chart from the book. So it says when to use the Z or the T distribution for that value. So basically it's one question, is sigma known or is the population standard deviation known? And if it's a yes, then you're going to use the Z scores in that chart with the standard normal distribution. If it's not known, you're going to be using the T distribution with the chart that we just introduced. So, simple question. All you have to ask yourself is one thing. Do I have the population standard deviation? If it's a no, it's going to be the T distribution. If it's a yes, it's going to be the Z distribution. So I threw that in this PDF, and yes, you can use that on the exam. So I'm being generous. So I threw it in here. Okay. Right, so that's our formula. So it is the mean plus or minus that T multiplier times the sample standard deviation divided by the square root of the sample size. And then just a reminder that to actually find the T value here, that you need the degrees of freedom. So you need the confidence and the degrees of freedom. So just remember that the degrees of freedom are n minus 1. So when you have your sample size, your degrees of freedom is just 1 less than that. Let's try this example here. It'll probably look very similar to what we've done in the past. So our example is a sample of 6 college wrestlers had an average weight of 276 pounds with a sample standard deviation of 12 pounds. Okay, let's just stop and go ahead and write down some of the things we know right there. So this should say X bar, and this should say, okay. So first of all, we are given the average weight of a sample. So we're given the sample mean, which is 276. So that's going to go here. And then we're also given the sample standard deviation of 12. So that's what X is equal to. Okay, so that's all we've got from the first sentence. Find the 95% confidence interval of the true mean weight of all college wrestlers. If a coach claimed that the average weight of the wrestlers on his team was 310, would the claim be believable? Good question. Well, we're going to find out. Okay, so first of all, we want to know N, which is our sample size. So we were told that the sample was 6 college wrestlers. So N is going to be 6. Okay, and then we're told that we want a 95% confidence. So we need to use that chart to figure that out, but we'll also need the degrees of freedom. So remember the degrees of freedom is going to be 1 less than N. So 6 minus 1 is 5. All right, let's turn to our chart. Okay, So we're looking at 5 degrees of freedom and 95% confidence. So that's going to land us at 2.571. Okay, and now we're just plugging these things into our formula. So our formula is x bar plus or minus t sub alpha over 2 times s over the square root of n. And that's equal to 276 plus or minus 2.571 times 12 over the square root of 6. Okay, so we know, or we're 95% confident that the mean lies within these two values in our interval. So we know that the lower value is 276 minus 2.571 times 12 over the square root of 6. And we know that the mean is then hopefully less than 276 plus 2.571 times 12 over the square root of 6. All right, so I'm going to let you guys attempt to simplify this. So go ahead and simplify both sides and then private chat me your answers when you get them. Just round to a whole number. Since we're dealing with like average weights, just give me whole numbers. So go ahead and give me in a private chat what these simplify down to. Okay, so I got some answers in. They look good. So this lower one is 263 and this upper one is 289. Awesome job, everyone. So let's go ahead and do the next example, which is slightly different. Also, on an exam situation, when I'm asking you something like this, I'll probably tell you what I want you to round to. So I'll probably say like round to 1 decimal place, round to, 2, whatever. Okay, let's do this next example. There's a little more work involved here. Oh, not what I meant to do. So same process, we just have to do a little more work in order to find the sample mean and the sample standard deviation. Okay, so for this, we're going to need the sample mean, but we're not just given it. So the problem says the following data represents a random sample of the number of home fires started by candles for the past 7 years. Find the 99% confidence interval for the mean number of home fires started by candles each year. Okay, so we don't know, we're not just told, oh, here's the mean of a sample. We're actually given the sample, which means that we just need to compute the mean ourselves. So remember, the mean is just summing up all the numbers and dividing by the total of the numbers. So let's just sum all these up. So I'm just going to add these numbers up using my calculator. Okay. Okay, so when I add them all up, I get 49,290. And then I just need to divide by 7 because I have 7 points in my sample. And this gives me a final answer of 7,041.4. Remember that when we're computing a sample mean, we give one more decimal place than the data points have. So our data points don't have any decimal places. So for the mean, we're going to give one more decimal place. So I'm going to round to just one decimal. Okay, so now we also have to compute the sample standard deviation. So this does take a little more work than the mean, but we have this little like shortcut formula. So if you remember, if we're doing a sample standard deviation, we know this is equal to the square root of the sum of all the samples squared minus the sum of the samples then squared divided by n over n minus 1. So we need to go ahead and do that for these samples. So, I could take the time right now to do it and plug it into my calculator, but I calculated it ahead of time. So I'm just going to write it down and trust that you guys know how to do this because we did it in a few chapters ago. So if you go through this formula and plug in the points, this gives you 1,610. Okay, so that's really how this problem differs from the last one, is that you have to calculate the sample mean and the sample standard deviation. I might give you something like this on the exam because, like I said, this class really builds on itself, and like we talked about how to compute the sample mean and the sample standard deviation. So that's something in the past that we've done, so you should still know how to do that. So I might give you something like that on the exam, like similar to this problem. Okay, well, our n is just our number of points, and we have 7 of those. And then our degrees of freedom is 1 less than the number of points, so it's just 6. And then we need to turn to our chart to find this t sub alpha over 2 value. So we want a 99% confidence interval. So let's use that and the 6 degrees of freedom and go find that value. Okay, let's see. 6 degrees of freedom. So we want 3.707. Okay, so now we just have to fill this into our formula. So I'm actually going to let you guys do this. So here's some practice because this is our last example on this lecture notes. So I'm going to let you attempt the rest of it. So I've filled in what you have. So using the formula x bar plus t sub alpha over 2 times s over the square root of n. Go ahead and, plus or minus, go ahead and give me the confidence interval. So compute the two endpoints of this interval, and let's say round to 1 decimal place. And then private chat me your answer. All right, awesome. So I did get some answers. Great job, everyone. So let's just go ahead and go through it as a class. So filling this in, we have 7,041.4 plus or minus 3.707. Sorry, times 1610.3 over the square root of 7. And this just ends up being 7,041.4, not a plus, minus 3.707 times 1,610.3 over 7 is less than mu, which is less than 7,041.4 plus 3.707 times 1,610.3 over the square root of 7. We get 4785.2. And this time I just put 1 decimal place. But like I said, on a quiz, I'll tell you what I want. Or on a test, I'll tell you. And that is it. So that is everything for section 7.2. So 7.2 is really just how to find the confidence intervals when you don't have the population standard deviation, when you only have the sample, and we can use what's called a t-distribution. So that's really the difference between 7.1 and 7.2, but you can probably see how similar everything else is besides like what chart you're using and stuff. Any questions on 7.2 before we just keep going and finish 7.3? Okay, let's go to our next section. Oh. Okay, section 7.3, only 2 pages again, so we'll probably finish this early. 7.3 is just on confidence intervals and sample sizes. So this same stuff we've done the past 2 sections, but for proportions, which now hopefully like this is aimed at those people that are doing their research questions with proportions. So now we're getting into some stuff with proportions. We've been talking a lot about means, but now we're actually going to do some stuff with proportions. So if you chose to do your research question with proportions, this is for you. So pretty similar, except for proportions, we're going back actually to using the z distribution, so the standard normal values. So we're going back to using that. So the only time that you're going to use the t distribution values is when you're using the sample standard deviation. Okay. So first, let's kind of talk about what a proportion is, because we really haven't introduced that at all, or like defined it, or really used a proportion. I mean, I guess we kind of used proportions when we did probability, but we didn't really like define like them as proportions. So let's go ahead and do that. So it says recall, but we have not talked about proportions before. So don't recall this. This is new. So we symbolize a population proportion by P, which seems appropriate since the word proportion starts with P. And then the point estimate. So if you remember, we talked about point estimates, I think on Tuesday. The point estimate of a population proportion is just a sample proportion. So similarly to how we said the point estimate for the population mean was a sample mean. So for large random samples, the central limit theorem tells us that the sampling distribution of the sample proportion is approximately normal. The distribution will have mean P and a standard deviation of PQ over N. Okay, so now we're going to define our confidence interval, which is our point estimate plus and minus our margin of error. So really similar to the last confidence intervals we've done. So we're going to be taking this point estimate and just subtracting and then adding this margin of error, which will be found in a similar fashion to the other times that we've done this. So the convention is that we will symbolize the sample proportion by p hat. A really original name, p hat. So p with a hat on it. So that is a sample proportion, and we symbolize it by p hat, and then the population proportion is just denoted by a p. All right, so now we have a formula, surprise, surprise. So here's our formula for a confidence interval for a proportion. So it is p hat plus or minus z sub alpha over 2 times the square root of p hat times q hat, which I will introduce what q hat is, over n. Where n P and NQ are greater than or equal to 5. Let's define Q hat though really quick. So Q hat is equal to 1 minus P hat. So this should kind of ring a bell when we did probability, and we would say that like if the probability of something happening was P, then the probability of it not happening was 1 minus P. So we would talk about like complementary or not complementary. I can't remember the word now. But we talked about probability complement. No, that's not it. I don't remember now, but you know what I'm talking about. Where we would say like the probability of doing this is like 1/4. The probability of it not happening is 3/4. 1 minus that. So should kind of ring a bell, and you'll see why it has like a similar look to it. Why we find Q hat by doing 1 minus P hat. So like I say, let's just do an example. But first, there's also a rounding rule, like always. So for a confidence interval for a proportion, you're going to round to 3 decimal places. We'll get right in, just try this. So in a survey of 935 people, 60% said yes, they believed in aliens. Calculate a 95% confidence interval. Okay, so first of all, some of my symbols are missing here. So P hat, Q hat, N, and then D sub alpha over 2. Okay, so first of all, we are given this proportion of people that believe in aliens, which is 60%. So it's a percent, so it's a proportion. So if you're given like a fraction or a percentage of people, that is your proportion. So 60% said they did believe in aliens, so our P hat is 0.6. And that's just because that was a survey of 935 people, so it was a sample. So the sample proportion is 60% or 0.6. So your Q hat is kind of like the proportion of people that said they don't, essentially. So 1 minus 0.6 is 0.4. So P hat is like your proportion of people that do, and Q hat is like your proportion of people that don't. Also probably kind of rings a bell to the binomial distribution. And then we have N, which is our size of our sample. So this survey was 935 people. And then when we do proportions, we use the Z sub alpha over 2. So we're looking to those values that we defined, I think, in section 7.1. So I'm just going to write these down as like a refresher. So we know that if it's a 90% confidence interval, that we're using 1.65. And then if it's a 95% confidence interval, yeah, good. Great question. So does that mean that if you know the P or the Q, the other one will be enough to add up to 1 with it? Yeah, perfect. So it's just like when we did stuff with the binomial distribution and we were like, oh, if you know P, you also know Q, because Q is just 1 minus P. Yeah, that is perfect. So if you do have Q or if you do have P, the other one is going to just be 1 minus the one that you do know. So great observation. And then we have a 99% confidence interval is Z sub alpha over 2 equals 2.58. So these are on your other notes. I'm just writing them down here so that you can refresh our memories. So since we're doing a 95% confidence interval, we're going to use the multiplier of 1.96. And per usual, now it's just a matter of plugging things in. So our formula is P hat plus or minus Z sub alpha over 2 times the square root of P hat times Q hat over N. And we have all these things, so now we just need to go ahead and plug them in. So this is 0.6 plus or minus 1.96 times the square root of 0.6 times 0.4 over 935, which is 0.6 plus or minus 1.96. Oh, not plus or minus, sorry. This side is minus. Times the square root of 0.6 times 0.4 over 935. And we want to be 95% confident that P, or the population proportion, lies within these two endpoints. So notice that now we're talking about P instead of mu. So instead of talking about a mean, now we're talking about a proportion. So we're using P. All right, well, did anyone happen to calculate this out and want to chat me what they got for their answers? You don't all have to do this. I'm just wondering if anyone did it already and wants to share what they got. Not that's fine. All right, that's okay, because I did it ahead of time. So if you use your calculator, you should get 0.569 and then 0.631. So these three sections are all extremely similar. It's just a matter of what distribution you're using and what stuff you're given in the problem. So if I was going to make my cheat sheet, my cheat sheet would definitely have like all of these formulas on them. And then that's like a lot of what you need for these. All right, so another example. So once again, I'm missing some variables here. So this is p hat, u hat, and then c so alpha over 2, and then this is okay, so this one says in a poll of 1,005 individuals, 452 thought they were worse off financially than a year ago. Find the 99% confidence interval for the true proportion of individuals that feel like they are worse off financially. Okay, so this is a good example to do because in the last problem we were given a percent. So we were told 60% of, now I don't even remember the problem. 60% of people said they believe in aliens. There we go. So we were given our proportion as a percentage, but in this one we're not. So we're given it as a fraction. It's just a little subtle because it says that the poll was taken by 1,005 people, and 452 of them thought they were worse off financially. So if we want the true proportion, or we want the confidence interval for the true proportion of people that feel like they are worse off financially, our P is going to be 400, or a P hat, sorry, P hat is going to be 452 over 1,005. So if you're ever given, if you're not given a percentage, but you're told like the amount of people that think this and the amount of people that were surveyed, your proportion is going to be the total amount of people that think it over the amount that were surveyed. And the Q is found the same. It's still 1 minus that. So if we do 1 minus 452 over 1,005, we should get 553. So this is 553 over 1,005. Because 452 said they thought they were worse off, which means that 553 said they were not worse off. And then our number of individuals that were surveyed is 1,005. And we want our confidence interval for a 99%. So if I come up here That means I'm going to use that multiplier of 2.58. All right, so now that I've introduced how this one's a little different, I'm going to let you guys try the rest of this one. So if it's a little easier to convert to decimal, you can. I tend to just use fractions to make sure that I don't round while I'm in the process, but proceed with caution. So go ahead and private chat me your two answers when you finish this problem, and I'll give you a few minutes. All right, so I did get some answers, so I'm going to go ahead and at least start writing what this should look like. So it should look like 452 over 1,005. minus 2.58 times, this is where my stuff's going to get a little messy because I used fractions, 452 over 1,005 times 553 over 1,005 over 1,005. Okay. Means P falls within here, and so my other side is, you know, I'm just going to get smart here. There we go. Step 4 plus. And then if you use your calculator, you get 0.409 and then 0.490, which are extremely similar, and I had to double take when I saw it, but that's that. Any questions on the last two examples? Because the last thing in this section is just to decide the sample size that you need. So just like we did in the last section, we're just going to be given a confidence and then decide what sample size is appropriate. Yes, it totally looked wrong at first when I looked at the answer. I thought it was almost the same number, and then I realized it was slightly different. So. Okay. All right, the last thing for today. So sample size for proportions. So just like before, sometimes we want to know the minimal sample size that's needed in order to give an interval estimate of some population proportion and be confident, or a certain level of confident in that estimate. So we have a formula that is derived from the formula that we've been using. So we get n is equal to p hat q hat times that z sub alpha over 2 over e squared. So remember, e is like that error that like you want to be within. So let's do this example. So how large a sample should be surveyed to estimate the true proportion of college students who do laundry once a week within 3.5% with 99% confidence? First of all, this problem is missing some information. So I'm going to add in something because it doesn't tell you anything about like the proportion of students that said they did laundry once a week. So you don't have a P hat or a Q hat. So I'm going to go ahead and just make one up. So we're going to say that a previous study shows that 55% did laundry once a week. So if you looked at this and thought, I don't know how to solve this because there's no P hat or Q hat, you were correct. So I'm just going to give you that proportion. So let's identify what's what. So P hat is going to be the proportion of students that do laundry once a week. So that's going to be that 55% that I just picked for fun. So that's going to be equal to 0.55. And then we know our Q hat is just going to be 1 minus that. So that's going to be 0.45. And then we also need that z sub alpha over 2, and we're doing a 99% confidence interval. So if we come up to our chart or our little thing here, that means that we need the multiplier of 2.58. And the last thing that we need is that E, which is like the error that we're kind of comfortable being within. So like this question says you want to get it correctly within 3.5%. So how large does the sample need to be to estimate the true proportion within 3.5%? So we want to be around 3.5% of the true proportion. So that E is going to be 0.035. Oops, I missed an equal sign. Because that is 3.5% just written as a decimal. So 0.035. And now all that's required is you fill in the formula. So we get n is equal to 0.55 times 0.45, and then 2.58 over 0.035, and then we just have to square that. And that's going to give you your sample size that you need. Okay, and I got an answer of 1,344.8. So this is, that was actually 0.9. But remember when we talked about sample sizes, we're always going to round up because we're talking about like the amount of people we might be needing to ask. So we don't like talking about a fraction of a person. So we're going to round up and say that we need 1,345. And that is our sample needed in order to be within 3.5% of the true proportion with 99% confidence. Okay, that is it for chapter 7. So chapter 7 is literally all on confidence intervals. So we are done for today. So I will stop sharing my screen. That is all of the content that will be covered on the exam. So it's chapters 5 through 7. Like I said, let me stop